Welcome, my fellow Voyager. Tonight we draw near to a horizon that is not a line but a feeling, a hush, where maps give out and the sea of time grows thin. Settle your shoulders, let the room grow still, let curiosity soften into wonder. Somewhere ahead lies a beginning that is not a bang in the air, but a swelling of space itself, a first light arriving without a lamp to hang it on. We will walk to the end of the pier by lantern light, slow steps on old boards, the wood cool and sure beneath the feet. Beyond the last post, the water is dark and patient. It is not empty, it is waiting. The question we carry is simple to say and vast to hold. What came before the Big Bang? If time itself is part of the unfolding, then before may be like north of the North Pole, a direction that softens as you approach it. Yet there are shapes the mind can cradle, a beginning without edges, a calm wind that smooths the early sea, a universe that holds its breath, then releases. So let the room grow still, let curiosity soften into wonder. As we set our course, I would love to chart our little midnight fleet, one lantern at a time. Let me know the hour you are drifting tonight, for it lets me draw a quiet map of when the world rests and guide future voyages to arrive as your night begins. And if these journeys bring you ease, a quiet like or a simple subscription will carry this small harbour of calm to others still awake. So, when you are ready, we begin a calm voyage through the greatest question ever asked. We arrive at the harbour where stories of the universe begin. The air is cool, the sea is calm, and a single lantern sways at the end of the pier. Beyond it, a quiet reaches further than any map, a dark that is not empty, only deep. The Big Bang is our best name for a very hot, very dense beginning of the cosmos. It is not a firework in space, it is the swelling of space itself. Galaxies do not fly from a centre, the distances between them grow as the fabric stretches. We know this not from guesswork, but from the faint afterglow that still bathes the sky. A low radio hush called the cosmic microwave background, a cool echo of an early, brilliant heat. Stand with me at this railing for a moment. Beneath us the tide moves, regular and slow. Let your breathing match the rising and fall of each wave. As you breathe, the story comes closer, gentle as mist. We can trace our universe back through time with measurements of light and structure. Stars form, galaxies gather. The first atoms join, and then the picture grows hot and bright. At some point the equations are clear and steady. Then they lead us toward an edge where our current understanding softens. Past that edge the numbers blur, not because there is nothing, but because our tools are not yet made for that water. What does it mean to speak of before when the story is about time starting? It is like asking for a place north of the North Pole, a direction that stops being a direction once you reach a rounded end. This is not a riddle meant to trick you, it is a clue about the shape of things. If time has a geometry, then beginnings may feel like smooth caps, not sharp corners. Let the image hold, a globe in your palm, smooth and complete. Slide your finger to the top, feel how every step north becomes smaller, how the compass quiets. Now imagine time with a similar roundness near its earliest moments, not a cliff, but a curve where simple words lose their grip. We return to the lantern because images help the mind rest while it learns. Think of the Big Bang as the instant the harbour lights came on. Before the bulbs warmed, the pier still existed as wood and rope and salt. Yet without light, your eyes could not name it. Physics is like that light, a way of seeing that needs instruments and theories to reveal what the dark already holds. Our instruments tell us that space expands, that the sky is filled with a whisper left from a time when everything was close and bright. They tell us that matter and radiation once moved as one hot fluid, then slowed and separated, allowing the first atoms to breathe into being. They tell us that structure grew from tiny ripples, as if a still pond had been tapped by a fingertip, and rings spread outward for billions of years. If the lamp is knowledge, then the pier is method. We walk it board by board, test by test, never running, never leaping into claims that shine too brightly to be true. In this way, science is calming. It does not promise what it cannot hold. It admits the mist and moves slowly within it. When people say there was nothing before the Big Bang, they usually mean something careful. They mean that our current theories describe time as part of the unfolding, like a thread woven into the cloth rather than a stage that was waiting. If the cloth begins to exist as it is woven, then asking about the state of the stage before the first stitch may not fit. The question is still beautiful. We simply learn to set it down in a gentler way. Let another breath rise and fall. Feel the weight of your body supported, the steady rhythm within your chest. This is the measure by which we will move, unhurried, patient, awake, and already drifting. There is comfort in boundaries when they are understood as shapes and not walls. A shoreline is a boundary that welcomes, a place where land and water meet and trade their stories. The earliest moments of the universe may be a shoreline like that, a curve where the language of everyday time gives way to a quieter geometry. From here we can see the paths we will take. One path follows a soft wind that could have smoothed the early universe, a gentle deepening we will call inflation. Another path circles around, beginning with no sharp edge, a way of thinking that removes the rim rather than builds a fence. A third path imagines the sea itself, taking a long, slow breath, a universe that compresses and opens in cycles that are more like seasons than endings. But that is for later chapters. Tonight, the first work is a kind of listening. We listen to what the sky tells us with its faint background glow, and to what the mathematics suggests with its curves and limits. We listen to the difference between what we know, what we think, and what we can only picture in metaphors that help us rest. Return to the lantern, see how it sways. The light is steady even as it moves. The circle it draws on the wood is calm and constant. Let your thoughts move like that, steady in their motion, untroubled by the dark around them. The Big Bang is not a noise to fear, it is a warm beginning that leaves a soft signature on everything. It is the reason the night between stars is not perfectly black, but carries a faint, even shine when measured with patient instruments. It is the reason galaxies arrange themselves the way frost arranges on glass, patterns born from small seeds in a cooling expanse. You do not need to hold every detail. Trust that the harbour will be here when you return, that the pier will keep its shape, that the sea will breathe in rhythm with you. Curiosity can rest without closing its eyes. It can breathe and wait and be ready for the paths that start from this quiet place. Let the final breaths of this chapter come like slow tides. In, a gentle swell. Out, a soft retreat. The lantern remains, the question remains, and the night keeps them both, patient and kind. Settle again at the end of the pier. The lantern is steady, the planks are cool, the tide moves in a slow and patient loop. We will look closely now, not at stars or waves, but at the thing that lets a story have a before and an after. We will look at time, as physics understands it, and we will do it softly. Time, in the language of modern physics, is not a metronome outside the world. It is one coordinate woven together with space, a thread in a four-thread cloth called space-time. An event is a point in that cloth, the way the tip of a needle touches a single place on a quilt. A life is a curve through the cloth, called a world line, and the length of that curve is not measured by footsteps or wall clocks, it is measured by proper time, the time that a clock carried along that curve would feel. You can picture proper time as a quiet tally the lantern keeps as it sways. The pier might have its own schedule, and the harbour master might shout the hour, yet the lantern knows only the rhythm it counts by its own pendulum. In relativity, every traveller is that lantern. Two people who reunite after different journeys will have tallied different totals, because space and motion bend the way their world lines lie through the cloth. Between any two events in space-time there is an interval, a measure that mixes distance and duration. In a calm, almost flat region, the rule looks simple. A square of distance minus a square of time multiplied by the speed of light. A careful bookkeeping that says light itself sits exactly at zero interval, neither ahead nor behind, always on the boundary. Those boundaries are light cones, the soft invisible lampshades that show which directions through the cloth are possible. Inside the cone there is a way to go and still be real. Outside it no signal can reach without tearing the fabric. Gravity, in this picture, is not a pull from afar, it is the shape of the cloth itself. Where there is mass and energy, the cloth curves, and where the cloth curves, world lines that would have been straight begin to lean. A stone dropped from your hand is not dragged through space by an unseen hook. It is finding the straightest path in a curved geometry, a geodesic, the way a ship on a globe follows a great circle, without ever feeling a push. The hush you feel in freefall comes from that straightness, a brief return to the natural line the cloth prefers. Let your breathing fall into step with this idea. In, the cone opens. Out, the cone narrows. What is possible at a place and time is set by the geometry, by the way the cloth is stitched, and by the constant speed of light that ties space and time into one measure. Cosmology asks a special question about time. It asks for a clock that many distant lanterns can agree upon, at least approximately, when they rest with respect to the great flow of galaxies. In our best large-scale model, space-time is described by a simple pattern called the Friedmann-Robertson-Walker geometry, a mouthful that means this. On the biggest scales, the universe is smooth, it expands evenly, and its shape can be characterized by a single scale factor that swells with time. You can picture that factor as the spacing between the planks of the pier, widening so gently that boards far apart part company more quickly than boards that are near. In that model, there is a natural time called cosmic time. It is the proper time kept by ideal clocks that drift with the general expansion, neither hurrying through space nor fighting the tide. Astronomers can almost join that rest frame by averaging over many motions, by listening to the faint afterglow that fills the sky and noticing how its whisper sounds slightly warmer in the direction we are drifting and cooler behind. When we subtract our local drift, we hear a nearly uniform hush. That hush defines the harbour's quiet hour. Cosmic time runs from an early hot state to the cooler, structured sea we live in now. Run the movie backward and distances shrink. Light grows bluer and more energetic. Matter and radiation blend into a smooth, bright fluid. Run it further, and the equations of general relativity keep guiding you, until densities and curvatures soar toward a regime where the cloth is no longer smooth thread, but something more granular and restless. The place where our classical description falters comes at a scale called the Planck scale, a size and a moment so small and so brief that our current looms cannot weave it clearly. About 10 to the minus 43 seconds after the start is where that blur begins, a number so tiny it is less a time than a whisper of possibility. It is here that caution is a comfort. When you hear the word singularity, think not of a point where the world ends, but of a sign that our map is overconfident. The equations are being asked to paint detail on a canvas they were not designed for. At such scales, quantum effects are expected to shake the cloth, to replace the smooth curves with a texture. Some proposals imagine loops of geometry, others imagine a foamy, fluctuating sea. All agree that new rules are needed, rules that let gravity and quantum theory talk in the same voice. What, then, does before mean in this setting? In the simplest reading of our standard model, cosmic time reaches a boundary where it cannot be extended with the tools we have. That boundary is like the rounded cap of a globe. You can walk around it forever without finding an edge, yet the direction called north fades to neutrality. To go beyond requires a new chart, a different coordinate, or perhaps a reshaping of the cloth that removes the cap altogether. We will meet such ideas soon, and we will treat them with gentle hands. There is more to time than the ticking of clocks. There is the arrow that tells you which way stories tend to run. The microscopic laws are mostly reversible. At the smallest scales, many processes can be played backward without violating any rule. Yet your tea cools, it does not warm itself. Memories collect in one direction. Waves spread and do not unspread. This is the thermodynamic arrow, the flow from low entropy to higher entropy, from fewer accessible arrangements to more. Entropy is not disorder as a scolded word, it is a count of how many ways a system can be arranged without changing what matters to your coarse glance. A freshly raked garden has few such ways. A wind-tossed patch of leaves has many. A universe that begins in a very special state, smooth in the ways that gravity cares about, will have room for history to happen. Clumps can form, stars can ignite, life can take shape. The arrow becomes the difference between a harbour before dawn and a harbour by evening, both calm, yet one holding all the waking of the day within it. Gravity complicates the story in a helpful way. A uniform fog of matter has low gravitational entropy because there are few ways to be uniform once gravity is allowed to pull. Let the fog feel its own attraction, and it can fall into countless clumped arrangements, galaxies, clusters, the lacework we map across the sky. Some physicists describe this with the language of curvature, noting that certain kinds of curvature were very small in the early cosmos, a condition that made the universe extraordinarily ordered in a specific sense. From such an initial calm, the arrow can run long and sure. The early low entropy is not explained by our ordinary equations. It is a condition set near the beginning that we read off from the sky, the way you can read last night's weather from the sheen on the pier. It might be the residue of a smoothing wind, like inflation. It might be a boundary condition written by a round start that has no edge to wrinkle. It might be part of a deeper symmetry, where time extends in both directions from a central hush, each side carrying its own arrow away from the middle, the way ripples spread out from a single touch and never need to cross back. Causality draws another map upon the cloth. There are regions that have had time to talk, and regions that have not. A particle horizon marks how far light has travelled since the hot beginning, a limit that says which lanterns could have coordinated their shine. The sky is astonishingly even, warmer by tiny parts in 100,000, a balance that seems to require early communication between widely separated patches. This is the horizon problem, and it asks for a gentle explanation. A short early deepening, a period of rapid stretching, could let once neighbouring waters drift far apart while keeping their temperatures aligned. We will walk that path next, like following a faint breeze across a quiet bay. Take one more breath and match it to the tide. In, the light cone widens. Out, the arrow points forward. Time in physics is a shape and a sequence, a geometry we can map and a flow we can feel. At the plank hush our charts grow pale, yet the harbour remains. The lantern sways, the pier holds, the sea keeps its patience. Settle again by the lantern and listen for a breeze you cannot feel on skin. It is a breeze from an older sky, a quiet wind that might have passed through the early universe and left it even and calm. We call that wind inflation. Not a blast, not a bang, but a gentle, relentless deepening that made space itself swell so swiftly that what was once near drifted far apart, leaving a uniform hush in its wake. In our maps of the cosmos, there are puzzles that appear as soft creases in a sail. The sky is almost the same temperature in directions that could not have spoken to each other using light alone. The overall shape of space is astonishingly flat, like the surface of a sea so broad that every wave seems level when you stand upon it. Heavy relics predicted by early speculative physics seem to be missing, as if thinned beyond sight. A brief era of accelerated expansion smooths these creases at once. Regions that were neighbours had time to settle into the same temperature. Curvature was stretched until it looked flat in every direction we can survey. Unwanted relics were diluted to whispers. The wind blew, the cloth evened, and the harbour became quiet enough for structure to grow later, slowly and sure. You can picture inflation as a still pond that suddenly, for an instant, deepens everywhere at once. Small ripples are carried outward and the surface becomes smoother to the eye, even though fine texture remains hidden within the water. Or think of a balloon painted with tiny specks. With each steady breath, the same painted patch looks flatter beneath your gaze, while specks that were once neighbours drift far apart without ever moving across the surface. Smoothing by stretching, calming by widening, order by a kind of patient enlargement. This is the character of inflation in its simplest form. What could make space expand with such insistence? In the language of fields, which are the soft underlayers of particles, imagine a field that stores energy in a way that hardly changes as it rolls. To help the mind picture it, think of a ball placed high on a very broad, very shallow hill. The slope is so gentle that the ball lingers. While it lingers, the energy stored by its height behaves like a uniform tension in space, and general relativity tells us that such tension produces repulsive gravity, not the pulling kind, but a push that makes the fabric itself accelerate outward. In physics classrooms, the ball is the inflaton field, and the hill is its potential. Here at the pier, it is simply stored height, lingering long enough to let the sea swell. As long as the slope stays shallow, the expansion remains accelerated. Space doubles in size again and again, not forever, just for dozens of doublings, enough to iron the creases. Then the slope steepens, the ball picks up speed, the stored energy is released into ordinary particles and light. This release is called reheating, and you can hear the image in the word. What had been a cold, uniform tension becomes a hot, lively bath of radiation and matter, the familiar fire from which the later universe cools. It is like water held high behind a dam being turned into motion, and warmth as it flows through the turbines and returns to the river. In this story, negative pressure does the quiet work. Pressure is not only a push you feel with your hand, it is a quantity that gravity can sense, a uniform energy that resists being compressed, a kind of cosmic tension, enters Einstein's equations with a sign that drives expansion faster. The details live in mathematics that most listeners need not hold. The shape of truth is enough. A gently rolling field, nearly constant in energy for a short while, can make the fabric of space swell as if it were breathing in, steadily and all at once. The wind did more than smooth, it sowed seeds. At small scales, fields cannot be perfectly still. Quantum mechanics turns any calm surface into something that trembles by amounts too tiny to see directly. During inflation, these microscopic tremors were stretched to astronomical sizes, like ripples frozen into the deepening pond. Where a ripple was a hair denser, gravity later had a head start. Matter gathered there first. Galaxies grew, as if following a faint, ancient score written into the water by the earliest wind. This is why the night sky carries a pattern that is both simple and rich. Measure the faint afterglow that fills space, the cosmic microwave background, and you find tiny variations in temperature, warmer and cooler by just a few parts in 100,000. They're almost the same strength on many scales, with a slight tilt that favours larger ripples over smaller ones. The pattern is close to Gaussian, the kind of randomness you get from many small contributions added together, the way raindrops make a soft hiss on the harbour roof. As the universe cooled, those ripples rang like sound in a warm plasma, creating a series of peaks in the pattern that careful instruments can read like notes on a staff. All of this matches what the inflationary wind would imprint, if it blew the way the simple models say. There is a deeper tone we are still listening for. An early rapid swelling could also send out a background of gravitational waves, the gentlest ripples in space-time itself. They would twist the polarization of the afterglow light into a faint swirl called a B mode, patterns too delicate to see with the unaided eye. Many teams have searched, and limits grow tighter. No definite note has been heard yet. The silence itself is a message, telling us the wind was not too fierce, or that the hill was not too steep, or that the story needs more texture in its details. Either way, the listening is patient and kind. There are open questions that rest softly in this harbour. What exactly was the field that rolled? Was it alone or part of a chorus? How did it begin high on the hill, And is that even the right picture at the deepest level? Some versions of the story suggest that quantum tremors could keep a few patches rolling forever, blowing bubbles of new space here and there without end. That idea points toward a larger sea, dotted with lanterns, which we will visit carefully when we speak of many possible universes. For now, it is enough to know that inflation explains much with a small set of moves, and that its edges remain under gentle, active study. Let your breathing match the calm of this picture. In, a smoothing wind. Out, a quiet sea, with ripples set for later growth. Inflation takes the horizon problem and makes neighbours of the early sky. It takes the flatness problem and stretches curvature thin. It leaves a pattern of seeds that we can still hear in the background light and see in the way galaxies are arranged across the dark. We will keep the balloon image and the pond and the ball on the hill because they are simple boats that carry us across a deep channel. For now, let the lantern sway. Let the tide move in a slow loop. Let the mind rest in the thought that the early universe may have been smoothed by a wind so gentle it can still be heard, if you listen with instruments patient enough to hear the hush. The lantern is steady. The sea is a single sheet of dark silk, and the pier feels sure beneath your feet. We are going to walk to a place where beginnings do not have rims. Not a cliff, not a sharp edge, but a smooth rounding, like the polar tip of a globe. There the word before loosens, and a different geometry carries the story. Physicists call this idea the no-boundary proposal. It is a way to say that the universe may have a finite, self-contained start without an initial boundary in time. Instead of a line that must be extended past a point marked 0, there is a surface that closes gently on itself, complete and rimless. You have felt a version of this when a path on a sphere keeps going until directions lose their bite and simply curve into stillness. North becomes a memory, not a destination. In the mathematics, time near the start is not the same kind of coordinate you know from clocks. The most helpful image is a quarter turn of the compass, as if the axis for time rotated softly into the axis for space. Physicists call this a Euclidean region, a patch where the geometry behaves as if time were another spatial dimension, smooth and without the sharp light cones that divide past from future. From that cap, the familiar time-like direction emerges, and the universe flows outward into the classical expansion we inhabit. There is no gate to pass, only a change in the way the cloth is stitched. The proposal is wrapped in a simple question, written in careful symbols. What is the wave function of the universe? In plain terms, what is the weight the laws give to each possible history that begins smoothly and rounds into an expanding cosmos like ours? To answer, the theory sums over compact regular geometries, favouring those that are simple and calm, the way the stillest waters add least to a boat's rocking. Out of that sum, the histories that look most classical are the ones that dominate, just as a clear melody stands out from a choir when the harmonies are tuned. To keep the picture grounded, hold a small globe in your mind. Let the south half be the Euclidean, rimless region, a bright, smooth shell. Let the equator be the place where the character of the geometry changes, and time as you know it enters the story. From that circle the universe expands like lines of latitude, spreading toward the north, each line a later slice of cosmic time. There was no earlier latitude because latitudes do not exist beyond the smooth cap, only a closed roundness that needs no additional coordinates to finish it. In cosmology, we reduce this to a single shape called the scale factor, a size that grows with time. Near the round beginning, the scale factor does not jump from nothing to something. It swells smoothly from a minimum, as if the globe's radius started at 0 and opened without a crease. In this calm, the early universe behaves very much like a de-Sitter space, a gently accelerating patch, which means the no-boundary idea sits comfortably beside the smoothing wind you met as inflation. The round start provides a natural, even stage. Inflation plays the first quiet movement upon it. Quantum fluctuations still have their part. Even on a polished shell, there are tiny tremors. When the universe rounds into classical time, those tremors ride along, stretched and imprinted as the seeds of later structure. The pattern they leave tends to be close to scale invariant, a simple fingerprint that says the largest ripples are only slightly stronger than the smaller ones. This is the same gentle tilt you have already heard about in the afterglow and in the web of galaxies. Different roots, similar melody. A phrase like no boundary can mislead if held too loosely. It does not claim that the universe appeared from nothing as a magician's gesture. It claims that the earliest region is complete without an edge that needs a rule pasted onto it from outside. The geometry closes in the past the way the surface of a sphere closes at the pole. There is no earlier place to stand, not because something is forbidden, but because the map itself changes character and has no more land to chart in that direction. To understand the flavour without the algebra, listen to the way the theory assigns weight. Histories that are smoother and more regular are favoured. Sharp corners, wild wrinkles, and violent oscillations are discouraged by the very way the sum is built. You can compare it to a path a ship might take across a bay. The water and the hull penalise sudden turns and reward steady arcs. When hundreds of possible routes are averaged, the calm curves dominate the average wake. There are neighbouring ideas that dress the beginning in different clothes. One suggests that the universe tunnelled, like a particle crossing a thin barrier, into expansion from a quiet, compact state. Another tries to specify a rule at the first instant that looks less like a rounding and more like a launch. These differences matter to specialists because they change how much smoothing the early universe prefers, and how strong any primordial gravitational waves might be. To the listener at the pier, the shape of truth is that several proposals try to remove the sharp edge and replace it with a principled hush. The no-boundary approach has been debated with care. Some worry about the stability of certain modes, about whether the sum over smooth histories is as well behaved as the poetry suggests. Others propose refinements that connect the early rounding to holographic ideas, where the deep interior of a space is encoded on a kind of boundary far away. These are active conversations. What remains steady is the intuition that a finite, rimless start can exist within physics without calling on an outside clock or a separate stage. There is also the arrow of time to hold gently here. If the start is round and calm, why does history run outward with such confidence toward higher entropy? One answer is that the rounding itself is incredibly special. It is smooth in the particular ways gravity cares about, keeping the early gravitational entropy low. From that low place, the arrow has room to lengthen. Another answer is that the arrow emerges only when the universe becomes large enough for certain kinds of records to form. So the sense of before and after is a property that condenses out of the expanding sea rather than a command written at the shore. Return to the lantern. Think of its circle of light as the portion of geometry we can see and test. The pier beyond the circle is not a claim, only a patient inference from the regular boards beneath our feet. When we look for evidence, we still listen for the same notes as before. A nearly uniform sky, a slight tilt in the primordial ripples, a softness in any gravitational waves that would have been made early on. The no-boundary picture does not shout new signatures. It offers a principled way to set the opening conditions before inflation's breeze begins to work. The comfort of this chapter is not certainty, it is coherence. A round beginning knits with the shape of relativity, with the idea that time and space are aspects of one cloth, and with the intuition that some boundaries are better understood as smooth closures than as cuts. If the universe began like this, it did not spring from an empty stage. It unfolded from a region where the distinction between stage and scenery did not yet exist, and where the cloth needed no extra seam at the start. Let your breath match the image. In, the globe smooths. Out, the lines of latitude spread. There is no hurry, only a geometry that rounds into the familiar, and a story that moves forward once time has a shape to live in. The lantern's circle rests on quiet wood. The tide draws in, then back, as if the harbour itself remembered how to breathe. Hold that rhythm. In, the sea gathers. Out, the sea opens. There is a family of ideas that gives the universe a similar breath. A long contraction, followed by a gentle release. Not a crack, not a tear, a bounce. When we ran our story backward through the equations of general relativity, we reached a boundary where the cloth was asked to bear more weight than it can. Classical geometry drives densities upward without limit until the map writes a singularity, a sign that we need a new chart. Quantum theories of gravity try to supply that chart. They give the cloth a texture, a granularity, a way for space and time to be made of something more than smooth thread. In several of these proposals, the texture becomes firm at extreme density. Compression meets a quiet resistance that is not present at lower scales. The result is simple to picture. The fabric refuses to fold into nothing. It slows, it steadies, and then it rebounds. Think of a net woven from tiny knots. Pull it gently, and it stretches. Pull it harder, and the knots tighten until the strands cannot be pressed any closer. They push back. In loop quantum cosmology, a model that applies quantum principles to the simplest large-scale universe, the knots stand in for chords of geometry. At very high density, an additional term appears in the cosmic bookkeeping, a contribution that acts like a soft repulsion. As the universe contracts and grows denser, this repulsion strengthens until the inward motion halts and turns outward. No point of infinite heat is reached, no edge is crossed, only a change in the sign of the expansion. What had been a gathering becomes an opening, in one continuous motion. The image is not a ball bouncing off a floor. There is no surface outside the universe to strike. The bounce is a property of the interior dynamics, the way energy, pressure, and geometry speak to one another when the cloth is almost too taut to bear. Before the bounce, distances shrink and the temperature rises. After the bounce, distances grow and the heat thins. Across the moment of reversal, the rules remain the same, only their balance tips. You can feel the comfort of that continuity. The harbour never leaves its place, it simply trades an in-breath for an out-breath. Contraction is not automatically friendly. Left on its own, a universe that shrinks tends to turn small imperfections into strong shears, the way a sheet of ice fractures along tiny weaknesses when pressed too fast. Anisotropies, directional differences in the squeeze, grow quickly during ordinary contraction. To arrive at a smooth bounce, something must tame those shears. Here is where an elegant idea enters, one that goes by a quiet name, ekpyrosis. Ekpyrotic contraction is a phase in which the content of the universe behaves with very stiff pressure, far greater than that of ordinary matter or radiation. Stiff in physics means the pressure responds strongly to compression. Under such conditions, the energy in directional shears drains away relative to the dominant stiff component. Imagine kneading dense, warm dough until all the errant bubbles are pressed out. The dough becomes uniform, heavy, calm. In the cosmos, the stiff component is modelled by one or more fields sliding down a steep potential. Their pressure so high that wrinkles and warp are ironed flat, while the whole sea continues to gather. This idea first grew within a picture of higher dimensional space, where our visible universe lives on a three-dimensional membrane, a brain floating in a larger volume. Two such brains can drift, approach, and gently collide. Their approach is the contraction seen by inhabitants on either brain. Their meeting is the event that ends the ekpyrotic phase and begins the release. To us it looks like a bounce. To the higher dimensional eye, it is a smooth encounter, a soft tap that warms the sea and writes new ripples into it. From ekpyrosis, one may imagine a cycle. Expansion dilutes and cools, structures form and age. A long, slow, dark energy era stretches the cloth until the observable patch grows almost empty to any one observer. Then a new ekpyrotic approach begins, smoothing away the last memory of old irregularities. The bounce returns the cosmos to a hot, dense state, ready to write another long chapter. The cycle is not a perfect loop repeating a single page. It is a series of seasons with a family resemblance, each new spring owing its calm to the deep winter that needed the sea before it. Such cycles face questions they address with care. Entropy tends to accumulate from one season to the next. If nothing removes it, cycles would grow messier and shorter. One remedy is the vast stretching during the dark energy era, which can dilute old clutter beyond any one horizon, resetting the local stage even if the global sea still holds every record somewhere far away. Another remedy is the ekpyrotic smoothing itself, which crushes the degrees of freedom that produce anisotropy before the bounce. The conversation is ongoing, but the melody is steady. Contraction can be made kind if the pressure is stiff and the approach is long enough. Bounces can leave signatures. They may not shout, but they can hum. Inflation predicts a nearly scale invariant spectrum of primordial ripples with a slight preference for large scales, and it allows a background of gravitational waves whose strength depends on the height of the hill the field rolled down. Ekpyrotic contraction tends to produce density ripples that are also nearly scale invariant but through a different mechanism, often involving two fields that trade their roles as the bounce approaches. In that trade, the statistics of the ripples can carry a distinctive skew, a mild non-Gaussianity with a shape that specialists can recognize if it is large enough. Gravitational waves tell a subtler story. In many ekpyrotic models, the stiff contraction suppresses these waves, leaving a cosmic background that is fainter than simple inflation might allow. If a clear, strong swirl pattern were ever seen in the polarization of the sky's afterglow, it would point toward an energetic inflationary wind, rather than a quiet ekpyrotic approach. If the swirls remain elusive and limits tighten, the bounce family gains room. Loop-based bounces, with their quantum geometry, can also imprint small oscillations or cutoffs at the largest scales, features that observers search for in the microwave background and in the clustering of galaxies. Hints have been reported and then softened by new data. Patience is part of the method. There are hybrid possibilities as well. A bounce could precede a short inflationary phase, borrowing the smoothing power of both. Or inflation might occur in a larger cyclic framework, with each cycle beginning with its own gentle wind. When models multiply, humility is helpful. We compare their quiet predictions to the quiet sky and keep only what remains after many tests. What matters for our harbour is the shape of time such ideas offer. There is no absolute beginning, only a minimum size, a slowest tide, a moment when the sea stops gathering and begins to open. Before that moment lies another chapter. After it, the chapter we inhabit. Memory may not pass easily across the turn, yet certain patterns could. A faint preference in how ripples line up. A suppression of power on the very largest scales. A quietness in the gravitational hum. These are soft clues we can listen for without losing sleep. Return to your breath. In contraction, out expansion. The bounce is not a reversal you would feel if you sailed through it. A sailor following the geodesics of the cloth would simply keep to the straightest possible path. Unaware of the sign change in the global motion, only the whole harbour knows it turned. We hold in one hand the round beginning that removes any rim. In the other hand, the bounce that trades a singular edge for a smooth turn. Both are ways of keeping the cloth intact. Both sit comfortably beside the smoothing wind, which can operate after either start. They differ in their signatures, in their metaphors, and in their mysteries. All are kept warm by the lantern of evidence, which brightens slowly, year by patient year. The lantern's glow is small, yet it reaches the rail, and the rope, and the quiet water. Tonight we let that circle touch a shoreline that may connect not just one ocean, but many seasons of a universe. Physicists call these seasons Aeons. Each Aeon begins hot and smooth, expands and cools, builds stars and black holes, and ends in a thin, patient light. Then perhaps there is another beginning. The idea has a careful name: conformal cyclic cosmology. Conformal means that angles are preserved even if sizes change. Imagine a map drawn without rulers, a chart that keeps the shapes of corners and crossings but forgets their scale. On such a chart, a small triangle and a continent-sized triangle can be matched because their angles agree. Cyclic means that one great season follows another, not as a loop in time you could sail around, but as adjoining chapters whose last page can be laid gently against the first page of the next. The heart of the idea is a boundary that does not feel like a wall. Penrose proposes that the very distant future of our universe, when only radiation remains, can be reshaped by a conformal transformation so that it looks like a smooth beginning for the next eon. Why radiation? Because massless particles do not carry a built-in scale. A photon cares about direction, not size. If everything that remains is massless, then stretching or shrinking the picture does not change the physics that light experiences. Angles are kept, rulers are forgotten. With that forgetting, the infinite future of one eon can be fitted mathematically to the finite beginning of the next. To see how a universe might become scale-free, walk the timeline forward. Stars exhaust their fuel, galaxies thin, and the expansion driven by dark energy makes distances double again and again. Most matter becomes bound into black holes, especially the giant ones at galactic centers. On vast timescales, those black holes evaporate by Hawking radiation, so slowly that the numbers feel like poetry. Trillions upon trillions of years pass until even the largest holes are gone. What remains is an extremely cold sea of photons and other effectively massless quanta, thinned by expansion, but not diminished in their angles. Without masses, there are no clocks that must tick at a particular rate, and no rods with a fixed length. In that sea, the notion of scale loses its bite. Conformal geometry reshapes such a sea without breaking its light-like structure. If you take a spacetime and multiply its metric by a smooth positive function, you keep the paths of light the same, though you change lengths and durations measured by massive clocks. This is the move that lets the distant future of one eon be pressed by a suitable conformal factor to touch the beginning of the next. Null geodesics, the tracks that photons follow, carry through the matching. The shoreline between eons is called conformal infinity on one side and the Big Bang on the other, and the mathematics asks that they be of the same smoothness. There is also the matter of gravitational texture. Penrose has long emphasized a distinction between two kinds of curvature. Ricci curvature tells matter how to move. Whale curvature carries the free tidal distortions that can exist even where matter is absent. His Whale curvature hypothesis says that near the Big Bang, Whale curvature was essentially zero, a way of stating that the initial gravitational degrees of freedom were highly ordered. This low gravitational entropy sets the arrow of time. In conformal cyclic cosmology, the distant future of an eon, after black holes evaporate, and after their interior degrees of freedom are gone, also loses its Whale texture. With Whale curvature suppressed at both ends, the conformal matching is smooth. The end of one eon and the start of the next share the same kind of calm. Does this remove the need for inflation? Not necessarily, but it offers a different route to smoothness. In CCC, the enormous late-time expansion of an eon and the loss of gravitational degrees of freedom can prepare a uniform, low-Whale boundary. When that boundary is conformally attached to the next eon's beginning, the new cosmos inherits a high degree of smoothness without an early rapid wind. Some versions of the theory try to account for the seeds of structure by processes in the final stages of the previous eon, a transfer of faint patterns across the boundary. Others allow a short inflationary phase within the eon and use the conformal matching as a broader frame. The melody is that the boundary conditions do a large share of the early work. If echoes pass across the shoreline, what would they look like? Penrose and collaborators suggested that violent events late in an eon, such as collisions of supermassive black holes, might send out spherical bursts, whose trace could cross the boundary and slightly modulate the temperature of the cosmic microwave background in the next eon. One proposed signature is sets of concentric circles with unusually low variance, like rings faintly drawn on the afterglow. Searches have been carried out with microwave background maps. Groups have reported hints. Other teams, using the same data with different methods, have found no significant signal. The discussion remains careful and unresolved. The quiet truth is that if such rings exist, they're subtle, and if they do not, the absence constrains how strong any cross-boundary memory could be. There is also the question of gravitational waves. Because conformal transformations preserve light-like structure, a background of very long wavelength gravitational radiation from the previous eon could, in principle, imprint delicate correlations in the earliest light of the next. The patterns would differ from those expected from simple inflation, likely fainter and with a different scale dependence. Current limits on primordial B-mode polarization in the microwave background already press many models. CCC accepts that pressure and reads it as guidance on how gentle any carryover must be. Entropy asks for its accounting as well. In ordinary cosmology, the entropy budget is dominated by black holes. In CCC, those degrees of freedom are said to be erased by evaporation before the matching, returning their energy to the sea of radiation that does not remember scales. Some physicists argue that the information in those holes must be preserved in the outgoing radiation. Others allow that the conformal boundary does not support any practical recovery. CCC takes the large-scale view, focusing on the gravitational degrees of freedom that set the whale texture rather than on the microscopic bookkeeping of individual quanta. The arrow of time in each eon points away from its boundary into increasing structure, even though the boundary itself is conformally smooth. A technical note rests gently here. To attach two eons conformally, you choose a function, often written as omega, that goes to 0 at the Big Bang and to infinity at the previous eon's future, or the other way round if you prefer the inverse. The product rescales the metric so that the two surfaces meet as one smooth seam. Time-like intervals do not carry through because masses do not exist at the seam. Null intervals do because light does not care about the rescaling. It is a precise way to say that rulers are put away at the shoreline while angles and light paths are kept. What of the small tilt in the primordial ripples that we measure so well? CCC must recover that feature too. In most versions, it arises from quantum fluctuations made classical at or just after the boundary, possibly influenced by the lingering radiation background from the previous eon. The details are active research. The requirement is clear and kind. Any successful theory must reproduce the nearly scale-invariant spectrum of temperature variations in the cosmic microwave background and the measured pattern of acoustic peaks. CCC treats those as constraints, not optional flourishes. Keep the images close as the science grows. Picture eons as adjoining seas that share a shoreline, where waves become pure direction, not size. Picture the wild texture as patterns in the surface of that water, absent at the boundary and free to grow far from it. Picture black holes as repositories for gravitational roughness that, with time beyond measure, return their energy to the light and leave the surface smooth again. There are open questions, and they are gently acknowledged. Do particles truly lose their effective masses as the eon ages, in a way that justifies the scale-free assumption? Which fields carry the continuity of patterns across the boundary? Are the proposed rings or correlations in the afterglow real or mirage? The answers are being sought with instruments that listen to the sky's hush and with mathematics that respects the cloth. Let your breath fall back into rhythm. In, a season expands. Out, a season fades to light. Conformal cyclic cosmology offers a picture where there is no final night, only the soft brightness of an end that can be matched to a beginning. It is not the only picture, but it is a coherent one, and it folds time into a geometry that the mind can hold without strain. The lantern's circle rests on the planks, and beyond it the harbour is a dark field with hints of distant lights. Hold that image. Each light is a possibility, a patch where physics may rhyme with ours, or change its key. This is the multiverse in its quietest form, not a promise, only a framework that grows naturally from the same wind that smoothed our early sky. In inflation, a field stores energy the way height stores water behind a dam. While the field lingers on a shallow slope, its nearly constant energy drives accelerated expansion, a de-Sitter-like swell where space doubles again and again. Quantum mechanics refuses perfect stillness. Tiny fluctuations nudge the field up or down from place to place. Where the field rolls down, inflation ends, energy releases into particles and light, and a hot Big Bang begins. Where a fluctuation pushes the field back up or keeps it high, the accelerated swelling continues. The swelling outpaces the endings. This is eternal inflation, a process that never stops globally, even though it ends locally, creating many hot regions that cool into distinct cosmic patches. There is another route to many patches, and it sounds like a soft pop. If the field begins trapped in a false vacuum, it can tunnel quantumly into a lower energy state by nucleating a bubble. The Coleman de Lucia picture treats this as a finite action event, like a droplet appearing in supercooled water. Inside the bubble, inflation can end and reheating can occur, lighting a new hot universe. Outside, the false vacuum still inflates, birthing more bubbles over unthinkable times. Each bubble interior evolves like an open Friedman-Robertson-Walker cosmos, with spatial curvature that is negative in principle, but can be stretched so thin by any internal slow roll that it becomes hard to detect. If many hot patches form, could their physics differ? In high-energy models, the field that drove inflation is part of a larger landscape of fields. Different regions can freeze into different minima, setting distinct values for masses, couplings, or even the effective cosmological constant. String theory sketches a very large landscape of such minima, stabilized by fluxes and shapes of extra dimensions. The result is not a single law book with one set of numbers, but a shelf of related volumes, each volume consistent, each volume local. Selection then enters softly. Observers arise only where conditions allow long-lived stars, heavy elements, and chemistry. This is anthropic filtering, used cautiously, as a way to explain why our measured vacuum energy is so small, yet not exactly zero, a value that permits galaxies to form before accelerated expansion thins the night. The framework brings precise questions. How do we assign probabilities in a setting that produces infinitely many regions? Naive counting fails because every outcome occurs infinitely often. This is the measure problem. Physicists test cutoff rules that weight events by what a single world line can in principle encounter, or by finite time slices tied to local expansion, seeking prescriptions that avoid paradoxes such as a preference for freak observers or unreal young universes. No single measure has universal agreement, but several avoid the worst pathologies and recover reasonable expectations for observations inside one horizon. Could other patches ever touch ours? Collisions between young bubbles are permitted in the theory. If a neighbouring bubble intersected our past light cone before recombination, it could leave a circular or disc-like modulation in the cosmic microwave background, a gentle bruise in the afterglow. Searches have looked for such azimuthal features and for a global negative curvature that an open bubble might imprint if internal inflation were short. No compelling signal has stood firm, and the limits push models toward either long enough internal inflation to wash away curvature or toward rarer collisions than our sky would likely remember. There is patience here. The silence narrows the space of possibilities without closing the book. Inflationary multiverses speak to gravitational waves as well. A high energy scale during the smoothing wind would create a background of primordial tensor modes. a faint twist in the polarization of the afterglow. Measurements have tightened the allowable amplitude. Lower bounds or null results do not disprove the framework. They shape the inflaton's potential, pushing it toward gentler slopes or multiple fields with shared work. Any future detection would set a scale and cut down the landscape, because not all potentials can sing that note and remain consistent elsewhere. There is a different kind of many that belongs to quantum theory itself. In the Everett view, when a quantum system interacts with its environment and decoheres, branches of the wave function support distinct classical outcomes that do not interfere. These are not distant bubbles in space, they are non-interacting histories within the same global state. Eternal inflation could coexist with such branching, giving a multiplication in both geometry and state. It is helpful to keep them conceptually separate. One concerns spatially disjoint regions with different low-energy parameters. The other concerns parallel records of outcomes under a single set of parameters. Both arise from taking our best theories seriously, and both are filtered by what we can observe from a single, small lantern. Testability asks for modesty. A multiverse is not a single theory. It is a family of consequences that follow from specific high-energy models of inflation and field dynamics. What can be tested are the pieces that touch our patch, the statistics of primordial fluctuations, any residual spatial curvature, the absence or presence of bubble collision imprints, the amplitude and scale dependence of primordial gravitational waves, the internal coherence of the measure used to make conditional predictions. Each is a quiet request to the sky and to the mathematics. Each can be answered without leaving the harbour. The lantern circle is small tonight, and it is enough. We have walked the pier through winds and roundings and long seasons, and now we stand where the question itself must be held with care. What counts as a beginning? In physics, beginning is not a single word, it is a family of meanings. A beginning can be a boundary in time that you cannot cross with any clock. It can be a place where curvature becomes so large that classical maps blur. It can be the moment when an arrow appears and memories become possible. It can be the first slice on which a simple rule is written, and from which histories unfold. Time as a coordinate is a thread in the cloth of space-time. When we ask whether time has a first stitch, we meet the notion of completeness. A space-time is geodesically complete if every free-falling path can be extended indefinitely in its own proper time. If some paths cannot be extended, we call the space-time incomplete, and we say there is a boundary, even if curvature stays finite there. Hawking and Penrose proved that with certain energy conditions, and with trapped regions or expansion of the right sort, classical general relativity points back to incompleteness. This is a mathematical way to say that the classical cloth, under those assumptions, cannot be continued forever into the past along every line. Yet the assumptions matter. Inflation, the quiet wind that smooths, violates the strong energy condition in a controlled way because a near-constant energy density acts like negative pressure. Different theorems then apply. Border, Guth and Vilenkin showed that any spacetime with a positive average expansion along a past-directed path is past incomplete. Eternal inflation in the future does not guarantee eternity in the past. That does not force a singular cliff. It requires that the inflating region taken by itself cannot be the whole story. A different phase must precede it, or the geometry must be rounded in a way that removes the rim. A bounce, an emergent static stage, a Euclidean cap, a conformal matching, all are honest replies to that requirement. We can soften the word singularity in one more way. A singularity in physics is a sign that a model was pushed beyond its range, not a promise that nature ends. Near the Planck scale, quantum effects should give the cloth a texture. In loop-based models, the texture resists unlimited compression and produces a minimum scale. In a no-boundary picture, the earliest region is not time-like at all. It is smooth and compact, so the request for an earlier tick is like asking for latitude beyond the pole. In conformal cyclic cosmology, the future of one eon, emptied of masses and scale, is reshaped into the beginning of the next. In each case, the aim is the same: keep the geometry regular, keep the rules coherent, remove the need for an external stage. A second meaning of beginning is the start of the arrow. Microscopic laws, in their most basic form, almost always allow a movie to be played backward. Yet the world we inhabit carries a direction. Tea cools, records are made, not unmade. Stars burn hydrogen into helium and heavier elements, and do not reverse that alchemy on their own. In cosmology, the arrow is explained by special initial conditions. The early universe was hot, yet gravitationally simple in a specific sense, with little of the free tidal curvature that would later appear as galaxies, clusters, and black holes. Call this the past hypothesis, if you like, a compact statement that the beginning was extraordinarily ordered by the standards gravity uses. From that low place, the number of accessible arrangements grows, and with it the capacity to remember. There are several ways to write such initial calm. Inflation can be read as a dynamical route to effective simplicity, since a brief era of accelerated expansion drives the large-scale geometry toward uniformity and flattens curvature. A no-boundary condition favours smooth, compact histories in the path integral, giving high weight to regular caps, from which classical expansion emerges. A bounce that includes a long, stiff ekpyrotic contraction irons out directional shears before the turn, leaving a state ready to expand without tears. A conformal boundary that matches massless futures to massless beginnings removes scales at the seam and erases the free gravitational texture there. Different stories, similar service, each providing a surface from which an arrow can run without contradiction. There is also the gentle possibility that the arrow points both ways from a central hush. In time-symmetric proposals, sometimes called Janus or two-sided cosmologies, the universe has a low-entropy middle and expands in both time directions away from it. Observers on either side would see their own past as ordered and their future as messy, and neither would have access to the other through ordinary signals. Quantum versions of this idea let entanglement play the role of the clock. A state with minimal entanglement between large subsystems can evolve so that entanglement grows in both directions, seeding two emergent arrows that never need to meet. The comfort here is that the arrow might be relational, a property of how parts of the world share information, rather than a command written into the sky by an external hand. Now we must speak softly about the problem of time in quantum gravity. When we combine quantum rules with the dynamical geometry of general relativity, the equation that describes the whole universe in simple models has no explicit time parameter. This is the Wheeler-DeWitt equation, written schematically as hp's equals 0, a constraint that says the allowed states of the universe are stationary in a particular global sense. How, then, does time arise? One answer is semi-classical. When the geometry becomes large and regular, the wave function separates into slowly varying background pieces and faster, light-like ripples. Along certain directions in configuration space, a parameter behaves like time for the ripples. Clocks inside the universe read that parameter as they interact and decohere. Another answer is relational. Choose a degree of freedom to serve as a clock, perhaps a scalar field or the volume of the universe, and describe everything else relative to it. The probabilities change as the clock variable changes, even though the whole state remains a solution to a timeless equation. In both views, time is not an external river. It is a pattern inside the sea, a regularity that appears once the water is calm enough for boats to keep a schedule. Decoherence plays a quiet part. Quantum possibilities branch when systems interact with large environments, and interference between branches becomes negligible. In cosmology, the environment can be the long wavelength gravitational field, or the sea of light itself. Classical behavior emerges when phases stop recombining, and records become stable. Histories then make sense, not as exact trajectories, but as sequences with high probability that fit together without contradiction. The arrow aligns with the growth of such records because records require free energy to form and are destroyed when entropy is high. A beginning in this sense is the time when records first become possible and remain reliable. A third meaning of beginning is the first simple rule. Cosmological models specify a geometry and ingredients, then write equations that say how they evolve. To speak scientifically about before the bang, we must either extend those equations through the earliest region or replace the earliest region with a principled condition from which the equations take over. Each candidate we have met makes a promise and faces a test. Inflation promises to smooth and seed, and it is tested by the spectrum of primordial fluctuations and by the search for a hum of gravitational waves. Observations show that the ripples are nearly scale invariant with a slight tilt and are close to Gaussian in their statistics. This is friendly to the simplest inflationary stories. The absence so far of a clear, primordial swirl pattern in the polarization of the sky pushes models toward lower energy scales or more intricate potentials. No boundary promises a rimless cap and a natural selection of smooth beginnings. It is tested indirectly by how easily it produces inflation and by whether the predicted distributions of perturbations match what we see. Bounces promise continuity through high density. They are tested by the specific shapes and small deviations they imprint in the largest scale variations of the afterglow and in the clustering of galaxies. Conformal cycles promise smooth seams and possible, very faint echoes. They are tested by the presence or absence of subtle rings or correlations in the background light, and by how well they reproduce the same acoustic structure that inflation handles with ease. No test is finished. The harbour is patient. There is one more theme, and it flows like dark water between all the lanterns. If the larger sea contains many patches with different local rules, the idea of probability becomes delicate. This is the measure problem. In an eternally expanding multiverse, regions grow without bound, and naive counting leads to paradoxes where typicality is ill-defined. Different cutoffs produce different answers to the same question. The scientific response is to tie probabilities to observables inside a single horizon, to restrict predictions to conditional statements about what we can in principle test, and to check that any proposed rule avoids pathologies. A beginning in such a setting is not a universal birthday. It is the first page of a story in one lantern circle, written by a rule that may be shared by many circles, or maybe one of many dialects in a larger book. So what came before the Big Bang? In one class of models there was no before because time is not defined in the rounded region that feeds the first classical moments. In another, there was a contraction, carefully smoothed, that turned into expansion, without a tear. In another, there was a previous Aeon, whose massless end became our scale-free start. In another, there was a larger space where inflating patches budded like lamps on a distant shoreline. In a few, there are two futures back to back, each carrying its own arrow away from a central hush. The choice among them is not made by poetry. It is made by quiet measurements of the sky and by the internal harmony of the mathematics that carries the cloth through its most delicate weave. Return to the pier. The lantern is steady. The sea is slow. The question is still warm in your hands. A beginning, in the language of physics, is the place where our best maps say the story cannot be extended without new rules, or where a principled condition takes the place of a missing chapter, or where the arrow first finds its direction, or where records first settle into place. Whichever picture is right, the night does not ask you to hold it all. It asks only that you let your breath find the tide, and let your thoughts drift to the edge of sleep.